So I want to talk first today about basic probabilities. Probability there's a lot of different definitions of probability, but really probability is nothing more than a measure of how likely something is to happen. And there's actually three main ways of measuring it. The names for it are kind of different depending on what textbook you're looking at, but they have the same thing. The first one is theoretical. Theoretical probability involves calculation and figuring out that way of what it should be. Most of the time when we're doing theoretical probabilities, we're looking at something called equally likely events. For example, if I'm rolling a die has 6 sides. Each side is equally likely to be the result of a roll. So I can use that knowledge to find the probability. The probability of rolling, that P with the parentheses means probability of, rolling a 2 was equal to, there's only 1 2 on that die out of 6 possibilities. So that's the theoretical probability, is the number of successful possibilities, successful outcomes we call them, divided by the total number of outcomes, number of total outcomes. So down here for rolling a 2, there's only 1 2 on that die out of 6 possibilities. The other is subjective. Subjective probability is based on past history. But it still involves some component of guessing or estimating. For example, any sports you're looking at, if they want to see the odds of one team winning or whatever, those are based on past history, based on these two teams playing before, both teams' record for the year, how they match up position by position. But there's still some element of guessing because there's still something about it that's not absolutely predictable. Kind of like horse racing would be the same way. I'm in the medical fields, same type of deal. Most of the statistics you get in the medical fields are between 2 and 5 years old. Well, we would like to assume, or like to hope at least, that the technology and the effectiveness of that treatment has improved over that period of time. So there's some subjectiveness involved in changing those estimates. Okay, 5 years ago, the survival rate was 28%. Well, what do we think it is now? So it's not absolutely based on calculation, but it's not totally a guess either. And the final one is empirical, or relative frequency. And all this is something has happened over and over again, and we've looked at the results and used those results to create the probability. For example, let's go back to that die. Let's say we roll that die 6,000 times. And our result out of those 6,000 rolls is 600 twos. So the probability of rolling, the empirical or relative frequency probability of rolling a 2, well, we got 600 twos out of 6,000 rolls. That's a 1 in 10 probability. So it's based on history rather than theory. This is often used on something like a die to test to see if it really is a fair die. When a die is manufactured, if there's imperfections in the material, air pockets in the plastic or whatever, it can be slightly more likely to come up certain numbers compared to others. Well, and if that's the case, you'd have to roll it several times and see. Here, out of 6,000 rolls, getting only 600 twos, it doesn't look good for that being a fair die. The biggest question there is how many times does it have to be rolled before we consider that relative frequency to be overtaking the importance of the theory. And there's we're not going to get into that conversation, but there is a whole muddy conversation on that, is how much history you have to have before you can say that it's not matching up with the theory. Some of the simplest examples of probability we can do are just marbles in a box. And we're going to put 50 marbles in a box. And what we're going to do is we're going to have 30 blue marbles and 20 red marbles. And we are going to say that when you reach into that box, it's blind, you can't see into it. That if you pull out a marble, each of those 50 marbles has the same chance of getting pulled out of that box. So we are going to be looking at theoretical probability here, rather than relative frequency. So let's say we look in that and ask ourselves, what is the probability of reaching in and drawing out a red marble? Well, in that box, there are 20 red marbles out of 50 total marbles. So that's a probability of 0.4. You could turn it into a percent and say 40% if you wish. Or you could ask, what's the probability of reaching into that box and pulling out a blue marble? Well, again, there is 30 blue marbles in the box out of 50 total. That would be a probability of 0.6, or 60%. So single events like that, single outcomes, they're called simple events, are pretty simple to calculate. Where it gets more complicated is if we look at a compound event. If I ask, what is the probability of reaching into that box, drawing out a blue marble, and then drawing out another blue marble? Well, it doesn't look that complex, but there is actually another question we have to answer before we can find that probability. And that question is the first marble put back? What does that mean? Well, it's talking about a term. The technical term is replacement or no replacement. When you have an experiment like this, where we want to know more than one result, 2 or more results happening along with each other or after each other. In this case, we're drawing out 2 marbles. We need to know, was that first marble put back in the box before we drew the second marble? Because if it is, that changes the probability compared to if it isn't. For example, let me show you here. Let's do this example with replacement. So drawing 2 blue marbles. So what that means is we reach in the box, we pull out 1 marble, we look at it, and then we put it back in the box before we draw the second marble out. So what is the probability? Now, for this to work, both marbles have to be blue. We're going to multiply the 2 probabilities together to get our overall probability. What's the probability that the first marble is blue? Well, we saw that up above, 30 out of 50. 30 blue marbles out of 50. Now, before we draw the second marble, we put that first one back in. So the probability that the second marble is going to be blue is the same, 30 out of 50. Those 2 events become independent. The probabilities don't change based on what happened in the first event. So 30 over 50, 3 times 30 over 50 is 900 over 2,500, or 0.36 probability. Well, what if it is without replacement? What this means is one of two things. Could mean we draw the first marble out, we look to see what color it is, then we set it aside before we draw the second marble. Or it could be we draw both marbles out at the same time. Now, either way, we're only going to look at them one at a time. So there's going to be a first and a second marble. So in this case, we still need both marbles to be blue. I always get asked, well, how do we know the first marble is blue? Well, we don't, but if the first marble isn't blue, then we're done. We don't care anymore. So we have to assume the first one is blue so that we can keep going. So there's a possibility of success. So here, the probability that the first marble is blue, well, we're still 30 blue marbles out of 50 total. So that's still 30 out of 50. But if it is blue, if it's not blue, again, we'd stop, we'd be done. If it is blue, we're not going to put it back. We're going to set it aside before we draw the second marble. So the probability of the second marble being blue is 29 out of 49, because that one marble is missing. So if we multiply that out, that's going to be 870 out of 2,450. If we divide that out, we get 0.355 probability. You can see just slightly less than if we had replacement. So this brings us to something called a conditional probability. In conditional probability, what we're doing is we're looking at two events. We don't really care about the probability of the first event. What we care about is how that first event changes the probability of the second event. So I'm going to do this. The probability of the second marble being blue, this symbol means given the first is red. So if the first marble is red, what's now in the box? Well, we draw out one red marble. That means we have 19 red in there and still have 30 blue. We didn't touch the blue. So the probability of that second one being blue, given that the first one is red, we still have 30 blues out of only 49 marbles now. So that goes up to 0.612 is that probability. Okay, so that's the basics of probability. I want to take a look now at a little bit more complex application of probability that's a little bit more practical. When you see data displayed in a table, and it's the technical term for it is something called a contingency table. And these are used a lot in business, a lot in medicine, and it's to compare two things to see if there's a relationship between them. Two different variables. One example I like to use for a company, let's look at level of education versus type of employment. So let's say that we have employees that are high school diploma or less. We have employees that are a bachelor's degree. We have employees that are a master's degree. So that's their level of education up there. Over here is the type of employee. We have employees that work hourly, employees that are on commission, and employees that are on salary. So let's say that of students who have a high school diploma or less, we have 182 that work hourly. We have 9 that work on commission and 2 that work salary. Bachelor's degrees, we have 23 that work hourly. We have 11 that work on commission. And we have 14 that work hourly, or salary. Master's degrees, well, we have 12 that work hourly. We have 4 that work on commission, and we have 13 that work on salary. So we want to find some probabilities from this. To do that, we need to find totals in both directions. So by both directions, I mean we want to find the column totals. So adding them up this way, and we're going to find row totals. Adding them up that way. So let's go down this first column. 182 plus 9 is 191, plus 2 is 193. 23 and 11 is 34, plus 14 is 48. 12 and 4 is 16, plus 13 is 29. Going this other direction, I've got 182 plus 23 is 205, 217 it looks like there. 9 and 11 is 20, plus 4 is 24. 2 and 14 is 16, plus 13 is 29. Now I get a grand total down here in this bottom right-hand box. I better have the same total both directions. So let's check that out. Let's see, 29 and 24 is 53. 270, it looks like that way. Let's go the other way. 29 and 48 is 77, plus 193 is 270. So we know that, well, we're pretty sure that our totals are correct because we get the same grand total either way. So now looking at this table, there are a lot of probabilities we can ask. For example, we might ask, of course, our general statement, I'm going to put that at the top here, is going to be what is the probability that a randomly selected employee ... So our first question here is works hourly. So coming up here, here's the people who work hourly right here. Well, the total there is the 217 down here out of our grand total of 270. So that tells me that we have 217 hourly employees out of 270 total. We divide that out, 0.804. So 80.4%. Let's get rid of that, and let's ask a different question. What is the probability that randomly selected employee has a bachelor's degree? Well, here's the bachelor's degrees right here. That total would be the 48 out of the 270. So that would be 48 out of 270. We'll divide that out. You get 1.78, or 0.178, I should say, or 17.8%. So those probabilities are pretty quick and easy to find. Next, we're going to make it a little bit more complex. What's that probability of randomly selecting an employee works hourly and has a bachelor's degree? So let's go back up to the table here. Here's hourly. Here's bachelor's degree. Now it said and, so I'm only concerned with the ones that meet both. That's the 23 right here. So the probability of working hourly and having a bachelor's degree, well, there's only 23 out of 270. So 0.085 or 8.5%. Or we might ask, what is the probability that someone has a master's degree and is on salary? Well, let's go back up here. Here's salary. Here's master's degree. There's only 13 that do both. So 13 out of all 270 employees meet both of those requirements. So 13 divided by 270 is going to be 0.048 or 4.8%. Let's change it up a little bit. What's the probability that a randomly selected employee has a master's degree or works on commission? So let's go up here. We'll get rid of this. So master's degree is here. Commission is here. But I didn't say and, so I'm not just looking at the 4. I said or. So that means the 9, the 11, the 4, and the 12, and the 13. I could just add all 5 of those up if I wanted to. 9, 11, 4, 12, and 13. Of course, it's going to be out of the 270. Well, that's what, 20, 24, 36, 49 out of 270 is what that's going to be. So 0.18 something. 0.181. The other way I could have done it, rather than adding up all the individuals, is I could have looked at it this way. This is all the people that work on commission. This here, the 29, is all the people that have master's degrees. But if I add those two together, I get more than the 49 I had here. I get 53. Well, why is it more? Well, because these 4 here are counted twice. They're counted in commission and in the master's degree. So I could just add together the totals, the 24 and the 29, and subtract out the 4 that are in both. That's still out of the 270. So that would still be 49 out of 270, or the 0.181. Okay, now that conditional probability that we were looking at with the marbles. What is the probability, again, that a randomly selected employee has a bachelor's degree given they work hourly? So what does that mean? Well, it's important which one happens first. The next question I'm going to ask is, let's say, what's the probability a random select employee works hourly given they have a bachelor's degree? They look the same, but they're very, very different. So the top one here, given that they work hourly. What that means is we're not looking at the whole group anymore. We are only looking at the group that works hourly. How many of them have a bachelor's degree? Well, 23 out of the 217. So there's 23 with bachelor's degrees out of 217 that work hourly. The given means we're only focusing on those ones, the hourly employees. Gives us 0.106 or 10.6% if you want to do it as a percent. The other one here works hourly given they have a bachelor's degree. Again, it sounds the same, but it's very different. Now we're only looking at the ones who have a bachelor's degree. We want to know how many of them are hourly. Well, there's 23 out of the 48. So I divide that out. It's going to give me 0.479. Or if you want it as a percent, 47.9%. So very, very different. Here, we were narrowing our scope. So rather than looking at all 270, we were only looking at the 217 that worked hourly. Here, we were narrowing our scope, so we're only looking at the 48 that have bachelor's degrees. So again, what's the probability a randomly selected employee has a master's degree given they work on commission? So we'll go up here. Now, is our population limited to master's degrees, or is it limited to commissions? Well, we want to know what's the probability that they have a master's degree. So we're not limited to just master's degrees. That's what we're looking for, is the master's degrees. It's given that they work on commission. So that's saying we're limited to only those who work on commission. So there's 24 who work on commission, and out of them, 4 have master's degrees. So probability of having a master's degree given they work on commission is 4 out of 24, or 0.167. What is the probability that randomly selected student works on salary, or randomly selected employee, I should say, works on salary given that they are high school or diploma or less? So given that they're high school diploma means we're only looking at those that have a high school diploma. These here. What's the probability to work on salary? Well, there's only 2 of them out of the 193 that work on salary. So 2 out of 193. Which is 0.010, or approximately 1%. So you can see how these tables here, if you have contingencies, 2 different possibilities like that, can be very valuable. And one thing we can do is we can look at what are the probabilities on each column or each row to see if they're equally likely. If this is a independent set of data, I should say, if their level of education does not affect what type of job they have, what type of position they have in the company, the percent here of high school given, or the percent of hourly given that they're in high school, should be the same as the probability of hourly, period. Let me show you what I mean by that. So what is the probability that randomly selected employee works hourly compared to works hourly given they have a high school or less education? Well, we have 217 out of 270 is our hourly. If we divide that out, we've done this before, I know, but we'll do it again. 0.804, so 80.4%. Works hourly given that they're in high school, that's 182 out of 193. So 182 divided by the 193 total high schoolers, we get 0.943. So here, company-wide, it's only 80.4% work hourly. But of those who have a high school or less education, 94.3% work hourly, which would tell me that most likely where they work is affected, or what position they work in is affected by their level of education. In the medical field, this can be used to evaluate locations. For example, we might have 3 different locations. We'll call them A, B, and C. And let's say we're looking at OB, the OB wing. So we're looking at patients coming in to deliver a baby. And we want to look at their time of stay. So let's say 0 to 48 hours, because most places try to have you out within 48 hours now. Or more than 48 hours. So let's say that at location A, in the last month, we had 47 OB patients that were in and out within 48 hours, and we had 3 that stayed longer. At location B, we had 69 patients that were in and out, admitted or released within the first 48 hours, and we had 7 that were there for more than 48 hours. At location C, we had 28 patients that were released within the first 48 hours, and we had, let's see, 2 patients that were held longer than 48 hours. So again, our first step is going to be to find row and column totals. So here 47 and 3 is 50. 69 and 7 is 76. And 28 and 2 is 30. So that's 156 total if I add those all up. Going down the rows. 47 and 69 is 116. Plus 28 is 144. 3, 7, and 2 is 12. And that also adds up to 156. So our arithmetic seems to check out. What I'm going to do is I'm just going to write it right in the side of each of these here. What the probabilities are given and what the total probability is. See if one location is more likely or less likely to hold patients longer than 48 hours after delivery. So up here we have 144 out of 156. So 92.3% or 0.923 of their patients are released in the first 48 hours. So here it was 28 over 30. Should be 0.933, but we'll divide it out here just to be safe. 0.933. That's pretty close to our overall district average there. Here we had 69 out of 76. That might seem a little low. Let's see what we get. 0.908. So that's 90.8%, down from the 92.3%, but still not horrible. And here 47 out of 50, that is 0.94, so 94%. So looking at this, even though just looking at the raw numbers here, you know, they had more than twice as many that were kept longer than 48 hours at location B as there was at location A. It's still only a difference of basically 91% to 94%. So it's not a huge difference. So that's what these contingency tables and probabilities can be used for. Okay, so for the test coming up on Wednesday, the big things you will need to be able to do is you'll need to be able to calculate mean, median, mode, standard deviation. I didn't give you a terribly big set of numbers for the standard deviation, but just make sure you keep track. There are 6 steps for the standard deviation. Next, you'll need to be able to do z-scores. Use z-scores to compare unrelated data. I might ask, you scored, the example I had, you scored a 32 on the ACT or a 1600 on the SAT. Which is a more impressive score? And we use those z-scores to see who had the higher z-score. Or we looked at firing an employee. We use the z-scores to compare each employee to their own department to see who was comparatively worse. You have the empirical rule. Where the empirical rule is the bell curve. Remember, the middle of the curve, you put the mean in there. Then you subtract the standard deviation at each step going to the left. Add the standard deviation at each step going to the right. And remember, those percents in here are always the same. These are always 34%, 13.5%, 2.15%, and 2.35% and 0.15 out there. And your book uses slightly different percents. I think they use 34.13 or something like that. They're just using a more exact form of it. I'm rounding them off because in industry, this rounded form is the way this is usually done. Okay, from there, it's just some basic interpretation. We're going to be going with the short version of this test since we'll only have one class to do corrections on it if we need to. You will be able to do corrections, but like I said, most groups don't need to. Average score last semester, like I said, I believe was just under 96%. So does anybody have any questions on the material in preparation for the test coming up on Wednesday? Everybody's muted, so I hope that means there's no questions. Okay then, there is no new homework today. So all we have is to prepare for that test on Wednesday. Coming up on Friday, I will be there to answer any questions. Hopefully I'll have all the tests in and I can have them graded and returned to you by class on Friday. I will be there to answer any questions on corrections for the test, or we'll offer some extra credit questions for you that you can work on to see how you do to increase your grades if you'd like. Otherwise, we'll see you guys on Wednesday.